Here we are at chapter 14. We're still going to be talking about radicals as we were in chapter 13. With 14, we're going to go a little more in depth, and the main two takeaways from this chapter are how to convert a radical expression into an exponential expression. That's the first thing that we're going to get into. And then from an exponential expression back to a radical. So that's the one thing. So radical to exponential and back. And then the second thing is simplifying radical expressions. And we've already talked about a few simple cases from chapter 13. For instance, if we were given, let's say, the cube root of x to the third power, then we said that, well, the index tells us that if we have three factors inside the radical, identical factors, then we can take one outside the radical. So what we've done here is pretty much simplified this radical expression, or you could say you evaluated it. Now, in chapter 13, our root number, the index, matched all of the exponents. We didn't consider cases such as the third root of x to the fourth, and let's see, we didn't consider cases where there may be multiple variables with different exponents, such as this radical expression here. And there's a lot other ways to simplify radicals that we haven't talked about. And so that's sort of the second big idea with this chapter 14. Now, if you flip through the pages, you'll see that this chapter is pretty long, and so I'm gonna, to try to save us some time, I'm gonna work the examples. I'm gonna focus on those and leave it to you to read the information in the chapter, the explanation, and for you to sort of study the examples that are already worked out. And I'm going to focus on working the examples that are unworked. So with example 1, they're wanting us to compare the square root of 2 and 2 to the 1/2. Alright, and I'd already told you about this in the previous chapter. I gave you an alternate way, should you not have the function in your calculator. I gave you an alternate way to evaluate this radical. I told you that you could take the 128, and instead of placing it inside a radical, you could take the index, the reciprocal of it, and place it over the 128 as an exponent, and these would work out to be the same number. This would end up being 2. Now, here with the square root of 2, this is an irrational number. It turns out to be about 1.4142, I think. Alright, and I have a calculator, so I'll just go ahead and pull that up, and we'll compare the results of these two expressions. So on one hand we have the square root, let's see, square root of 2, enter, and on the other hand we have 2 raised to the 1/2 power. We get the same exact decimal number, approximately 1.4142. So we can write 1.4142 over here to 2 to the 1/2. Alright, if you can find a cube root button, which you may or may not be able to do, and that is the importance of this translating radicals to exponential expressions. Sometimes the calculator just doesn't have these higher index number radicals, so let me take a look on my calculator. Let's see, maybe math. Here we go. Math, in the math menu, number 5. We have, let's see, it's asking us for the radical, and we can sort of scroll our way up here and change the root number, and then inside we can place the radicand 3, and we get 1.4422. Alright, now that was kind of tedious to hunt down this particular function, change the root number, the 3, and then put the radicand inside it, the other 3, and calculate it, when we could have just took a 3, raised it to a power of 1/3, enter. It's a little quicker, but you can see that we get the same result, 1.4422497. Alright, now as you probably already guessed, the fourth root of 4 is going to end up being exactly equal to 4 to the 1/4 power. So what happens, what did we observe? What happens with our root number? It simply becomes the denominator of the exponent of the radicand. Okay, and now this 4 over here, we can sort of call it the base of our exponent. But you see what happens to the root number, the index number. It becomes a denominator in the exponent. Example 2, previous chapter, we talked about square roots, and this is where we sort of get into trouble. For instance, square roots, we said, well, the square root of 4 is 2. We talked about the square root, and I guess I could say the principal square root here, but that's usually understood when you see this radical. We talked about square root of 16. 4 times 4 is 16. This is the principal square root. And we saw 25. Square root of 25 is 5. Now, we ran into trouble when we tried to take the square root of a negative 4. We said that that was not real. It's not a real number. However, if we change the root number to a cube, and we toss a negative number inside the radical, for instance negative 8, we don't run into any problems. Okay, the answer to this is negative 2, and that's simply because if we take a negative 2 and we raise it to the 3rd power, we'll get back a negative 8. We can get this negative whenever the root number is odd, but without, and of course up here for these square roots, without an odd root number, when it's even, like this 2 was, we can't multiply a bunch of numbers together an even number of times and get a negative. It's always going to turn out positive. Alright, so this should give you a clue as to how to answer example 2. It says when is this expression in general. N could be any whole number. When we take the nth root of a number x, when do we say that x to the 1/nth power is not real? Well, to answer that, we should say if n is even, then x must be non-negative. And so with that comment, it sort of allows us to use this equation here freely. Up at the top, you'll see three different expressions that are all equivalent to one another. There's two radical expressions and there's one exponential expression. We want to take example 3, 4, and 5 and translate them into the other two expressions. So if you look closely at the equation given at the top of the page, you'll see that an exponential expression can be written in radical form. So here's our radical. But now we have to divide up this fraction and place the parts of it in the proper place. And the way we do that is we take the denominator, and that becomes our index. We take the numerator, and that becomes the exponent of our base. And here the base is x, 5/12 is the exponent. So x goes inside the radical, 12 goes to the index number, and 5 serves as the exponent of the x. So to finish this, we write 12th root of x to the 5th power. Now, this is one of the radical forms. A second radical form could be found if we were to pluck out the 5 from the x and write out the 12th root of x by itself and simply put the exponent 5 outside of a set of parentheses. So the 12th root of x to the 5th power is the equivalent of the 12th root of x times the 12th root of x 5 times. Okay. Now these two here are the ones that we were told to find. You don't actually have to write it out 5 times, but that, with this 5 here sitting beside these parentheses, it's telling you that you could write this out 5 times multiplied. Okay. The next one, we're given the radical expression. And what we could do is go ahead and write the other radical expression by pulling out the 3. Pull out the 3, place the radical with the index and the base, the m, inside a set of parentheses, and simply write the exponent outside to the right of the parentheses. So this would be a 4th root of m, and then all of that raised to the 3rd power. So this is the alternate radical version. And now we want to write it without a radical in exponential form. And we said the exponent of the m stays in the numerator, and the root number 4 goes to the denominator of the exponent. So m to the 3/4 power. The next one, you see that we have it written with parentheses and a 6 on the outside. We could take that 6 and pull it to the inside of the radical and attach it to the t. So this is the 7th root of t to the 6. And now we could drop the radical altogether, write t to the 6, and simply place the 7 underneath the 6 as a denominator. So in each of these examples we have all 3 versions. Alright, these 3 versions sometimes come in handy. Here we see 27 to the 4/3. which is somewhat mind-boggling if you were to try to calculate it only considering the exponential form. We know that, for instance, if we had 27, let's say it was raised to the, I don't know, third power. Okay. With a 3 there as the exponent, we know that we'd simply just write out 3 27s and multiply them together, and we could compute 27 to the third power. But how do we write out 3/4 27s multiplied by one another? How do we write this in terms of multiplication? I don't know. Okay, I don't think there is a way to only write this in multiplication. So, without these radical forms, we're stuck. Now, of course, you could stick this in your calculator and it would just spit out the number. But let's say, for instance, we wanted to calculate this by hand. One way would be to take the denominator of the exponent, the 3, write it as the index of a radical, place the 27 inside, and here's one radical version, but it really doesn't do us too big of a favor, because now on the inside we've got this 27 to the 4th power, and if you're like me, you're probably, you can't calculate that in your head. 27 to the 4th power is a big number, and you probably don't know the third root of whatever that number turns out to be. So we're not going to stop there. We are now going to write it in the other radical form, where we only leave the 27 inside the radical and we pull the 4 to the outside of the parentheses. Now, third power of 27, you probably should be familiar with that. 3 raised to the third power is 27, so our cube root is 3. A lot easier to evaluate when that number is inside the radicand is as small as we can get it. Now, this radical expression was replaced with 3. We have the 4 still waiting on it outside the parentheses. At this point, this just tells us that we have 4 3's multiplied by one another, which reduces to a 9 times a 9, and we see that it turns out to be 81. So 27 to the 4/3 power is 81. Okay, without the radical expressions, who would have guessed that? Alright, example 7. We have a -8 raised to the 2/3. We'll go ahead and write it in this radical form that we see right here, because this form keeps the number inside the radical as pretty much as small as we can get it. So we'll take the denominator, we'll write it as the root number of a radical, and then we'll take the 2 and write it outside the parentheses. The third root of a -8 is a -2, and a -2 squared is a +4. For the -16 to the 3/4 power, we write the 4th root of -16, and then we raise that to the 3rd power. So it gives us a different order that we can apply this 3 and 4 in. So we apply the radical first, 4th root of -16, and we run into a problem. This 4 is an even number, it's an even index, and we have a negative inside. And so what we have inside here is not a real number raised to the 3rd power. Okay, it's not going to turn out to be a real result. So we just sort of wave our hands at that. If we stick this in our calculator, we can see what happens real quick. Let's see. Parentheses, -16 to the 3/4 power You see, the calculator even tells you non-real answer. So we'll just hit quit. Okay, the next page. If we were to take these exponential expressions here that are multiplied by one another and write them as a radical first, we would end up with the fifth root of 2, and then we'd have the square root of 2. Now, written in this form, there is not a way that we can directly combine these into one radical. Now, you may have seen me break apart a radical in the previous chapter. For instance, we had an example of 4x squared inside of a square root, and I broke this apart into a square root of 4 and a square root of x squared. Now, likewise, for instance, if we were given the square root of 16 times the square root of, say for instance, y to the 4th power, then just as easily as we broke this square root apart into 2 separate square roots, we could multiply these two together and get a single square root of 16y squared. Now, what allows us to do that is that all of these radicals are based on the same index number. They're all square roots. These, in example 8 on the other hand, have different indexes. Okay, so there are quite a few more steps involved in actually combining these two exponential expressions. We have to fall back on a basic property of exponents that we learned in intro algebra. And that is, if the bases are the same as 2 is, okay, the base of this exponential expression is 2, likewise the base of this one is 2, we can combine these into a single 2 if we just add the exponents together. Alright, so remember the property, it's called the product rule of exponents. If we have two variables, same variables multiplied, then to combine them into a single one, we just simply add the exponents. And so here we get an x to the 5th power. That's the same thing that we're doing here with the number 2. Now, in this case, we can't outright add these two fractions. We first have to find the common denominator, which in this case will be 10. 5 goes into 10 twice. 2 times the 1 in the numerator adjusts this fraction to a 2/10. For the next denominator, the 2 divides into 10 5 times. 5 times the 1 gives us a 5/10. Now that the denominators are the same, we can add the two exponents and get a 7/10. And we have a single exponential expression that we can translate into a single radical. And we could write it as the 10th root of 2 to the 7th power. So, the next one, same procedure. We write a single b. We add the two exponents together. At this point, we see that they have different denominators, so we use a 6 as our lowest common denominator. The second fraction needs no adjustment. It already had a 6 as the denominator, so we keep the -5. The first one has a 3, so the new denominator gets divided by the old one, 3. 6 divided by 3 is 2. We take the 2 and multiply by the old numerator to get the new one, 4. Denominators are the same now, so we add 4 and -5 to get a -1. We keep the common denominator 6. if we wanted to get rid of that negative exponent, we would move the b to the denominator, and the exponent would become positive. And now we could write this as a 1 over a 6th root of b. Okay. Example 10. We have 1, 2, 3 a's. Now, the top two can be added together because they're multiplied. And now this one on the bottom, we can move it to the top so that we can combine it with the other a. And when we do, this 1/3 becomes a negative 1/3. Now, we'll take these two a's and combine them just like we did the 1/6 and the 1/4, and we'll write 1/6 plus 1/4 plus a negative 1/3. When you have several of the same variable multiplied, you add all the exponents. Alright, now our denominators are 6, 4, and 3. Common denominator would be a 12. 12 is the smallest number that 6, 4, and 3 will divide into. So that's what we use as our common denominator. 6 goes into 12 2 times. 2 times the 1 on the top gives us a 2. 4 goes into 12 3 times, and 3 goes into 12 4 times, but there is a negative 1 sitting right at the top of this fraction, so this would be a minus 4 over 12. Now we add the numerators. 2 plus 3 is 5, minus a 4 gives us a 1. We keep the common denominator 12, and now with a single exponential expression, we can write a single radical expression, 12th root of a. Denominator becomes the index. Alright, we want to use these formulas, 1 and 2, given above, to rewrite the expressions. So we either need to break it out, break it up, or recombine it. So here inside the radical, the 8 and the x squared are multiplied. We could break it up. It's already combined, so our job is to break it apart. That's all that we can do with it. Okay. In C, these are 3 separate radicals. We can go ahead and recombine them. 2ab under one square root symbol. Here we have a cube root. They're already combined into a single expression inside, a single radical. We'll break it apart. Cube root of t to the 6th power over cube root of 27. And now here in D, we have 2 separate radicals, square roots. We'll combine them into one and call this square root of 8 over 2. Alright, now, only when the radicals have the same root number and they are multiplied or divided can we do this. Okay, join the parts together into a single radical. Here we have a comment, and it's simply telling us that if we have 2 things added or subtracted underneath the radical, we can't break them apart in terms of the sum of the 2 radicals. Okay, you cannot break the sum apart as it is shown here. One way to check that would be to see if these 2 expressions are the same. Can we take a square root of 9 plus 16 and write it as the square root of 9 plus the square root of 16 separately? So if we add 9 and 16 inside the radical, we will get the square root of 25. Well, we already know that's 5. If we try to separate the sum into two separate radicals, we have the square root of 9 plus the square root of 16. The square root of 9 is 3. The square root of 16 is 4. So the right hand side of the equation becomes 3 plus 4, 7. The two sides aren't equal. That tells us that we cannot break apart the 9 plus 16 into separate radicals. Okay, now we're going to start getting into simplifying radicals a little more than we have, and we're talking about the first way to simplify here. And remember that we said, for instance, if we have a cube root of m to the third power, well, we have 1, 2, 3 m's multiplied inside. That's what m to the third is. The root number basically gives you a rule that says if you have 3 of any variable inside the radical, then you can strike those out. You can use up those 3, and you can, for those 3, you can move 1 to the outside. Now, for m to the third power, once we use up all the m's, all 3 of them, there's nothing left in the radical, and so we drop the radical. Okay. Now let's say, for instance, we had a cube root of m to the fourth power. Well, that would mean we had the cube root of 1, 2, 3, 4 m's. Well, we still have the rule here in our index number that we need 3. For every 3 that we can take out, that we have inside, we can take out 1 m. And to take out 1, we need 3. So we've used up 3, and we have 1 left over. So we took 1 out front, and this will become m times cube root of m. This one had to stay inside the radical. So we're left with a cube root here. We weren't able to get rid of it completely. Alright, the same rule applies to numbers. And of course you may say, well, with 50 there's only one number there, but what we can do is break 50 apart into its prime factors. And that's exactly what we're going to do. We're going to write 50 as a 2 and then 2 5s. So 50 equals a 2 times a 5 squared. And as you see here, we have a radical symbol with no index number written. That means we're dealing with the square root. The root number is automatically a 2. So if we have 2 of anything inside the radical, we can bring one of those factors outside the radical. So we have a 2 and then a 5 squared. This exponent here, the square, means that we have 2 5s. And so we're going to strike those out, and we're going to bring them out one, not both of them, just 1 5 to the front of the radical and write 5. But then there weren't enough 2's. We only have 1 2, and we need 2 2's to bring one out. So the 2 gets left behind inside the radical, and it has to stay there. So this simplifies to a 5 times the square root of 2. For 16, we have the cube root of 16, and a 16 is just 1, 2, 3, 4 2's. Alright, 2 to the fourth power. Well, we only need 3 to bring one out, so we'll strike out 3 of them, and those 3 allow us to bring 1 to the front, outside the radical. But there's 1 left inside, so we rewrite it as a 2 times the cube root of 2. This is our first method of simplifying radicals. reduce the exponents until they are smaller than the index number. Now, an x to the 11th can be broken up into an x to the third, an x to the third, another x to the third. So we've accounted for 3, 6, 9 of the 11 x's, and then what we have left over will go into the last exponent, an x squared. I broke it up into x to the thirds because our root number, our index number, is 3. So for each 3 of these x's, we can bring 1 out. So that's 1, 2, and 3. Okay, 3 groups of 3 x's. So our x in the front is going to be an x to the third, and an x squared gets left inside. So 3 x's in the front, and then we had the cube root left over because we weren't able to take all of the x's out, and inside there's an x squared. Okay, the next one, we have a 7th root, and so we're going to break these exponential expressions inside up into 7s. We can say we have an a to the 7th, and 7 from 8 leaves 1, and so we have an a to the 1 off to the side. B to the 24, it contains 3 b to the 7s, and 3 7s is a 21, so we have some b's left over from the 24 that we started with, and we have 3 exactly. So for each one of these, we can bring out an a here, a b there, and then 2 more b's. Alright, so we're going to strike these out, and inside the radical we'll have an a and a b to the third left over. So in front of the radical we'll write a and b to the third, 1a, 1, 2, 3b to the 7th, and then we still have our 7th root with an a and a b3 inside. Example 17, we need to take 54 first and break it up into primes. We have a 2, and we have a 27, and a 27 is a 3 and a 9, and then a 9 is a 3 and another 3. So here are the prime factors. So we'll rewrite the cube root of 54x to the 7th as a 2 times a 3 cubed, and then we'll break the x to the 7th up into powers of 3, x to the third and x to the third, so that accounts for 6 of the x's, and to make 7 we have 1 left over. Now for this 3 to the third, that means we have 3 3's, so we can bring a 3 out to the front of the radical. For each of these x to the thirds, we can bring out an x, and we have 2 of them, so that means that our x is going to be squared in the front. So we struck all of those out, we used them up, and we have a 2 and an x left inside the radical. So we write 3x squared, cube root, and a 2x inside. Example 18, we see that c to the 20th, 20 is divisible by 4 evenly. So we could write this out as we've been doing, C4, 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 and it'll break up into 5 of these. Alright, since we're multiplying all these c's together inside, then we can add the 4's together. If you add 5 4's, you get back your C20. So we broke this C20 up. for each one of these C4s, we can bring out one C. So that's 1, 2, 3, 4, and 5, giving us a C to the 5th power in the front. And when we strike all those out, there's nothing left. C to the 5th power. Now, an alternate route that you could have taken instead of breaking it up into all these C terms, it would have been to say, I can just translate this radical expression into an exponential one by writing my index number in the denominator of the exponent. So C to the 20th, 4 on the bottom, a 20 divided by 4 as an exponent is the equivalent of a 5 as the exponent. So, sort of a different way to work it. Now, once you've worked enough of these, this negative will jump out at you. It throws up a red flag in my mind, and so when I see a negative inside a radical, I automatically check this root number. If that root number is even index or root number, and negative inside, then you automatically just say, you don't even consider the variable of the exponent, you just say that the result is not a real number. Alright, our second way of simplifying radical expressions is to get rid of fractions. Now, at the beginning of the chapter we learned that we could break up a fraction that is inside a radical into two separate radical expressions like this. Okay? And each of these radical expressions can be rewritten in exponential form by writing the index number as the denominator. Same for the y on the bottom. 12 would be divided by 4. And you see that 4 divides into both of these exponents of the x and y evenly. We get a 2 as the power of the x, and we get a 3 for the y. And we do not have a fraction in a radical or a radical on the bottom of a fraction anymore. There is no radical left. Okay, so a lot of times all you really need to do is reduce the exponents inside to where they're less than the root number, and you won't be left with anything in the radical. They'll just completely disappear. That's not the case with example 22. Alright, the exponents are not evenly divisible by the index number, and so this is slightly more tricky. What we'll do is we'll work inside the radical first. And we'll take the numbers. 3 is prime, so you can't factor it. We'll take the 8 and we'll break it up into prime factors 2. And then this 4 gives us 2 more 2's. Okay, so I'll go back up here and rewrite my 8 as a 2 to the 3rd power. Now, as you should know, if you have a fraction such as 3/4, okay, I'm not with this 3/4, I'm sort of stepping to the side. I'm not talking about radicals here. I'm just talking about fractions in general. We can multiply the top or the bottom by any number that we want to adjust this fraction, as long as we multiply the other side of the fraction by the same number. So I could take this fraction and multiply both numerator and denominator by 3, and I'd get 9 over 12. If you put 3/4 or 9/12 in your calculator, you'll get the same number. So 9/12 is the equivalent of 3/4. I could take 3/4 and I could multiply it by 4 over 4. Anything I want to, as long as I multiply the numerator and denominator by that same number. I get 12 over 16. Okay, you put this in your calculator, you'll get 0.75. We haven't changed the number, we've just changed the denominator that it's based on. Alright, that is how we're going to fix this situation in example 22. We want all of the exponents to match the root number. That's our best situation that we can get when we're dealing with radicals. So here we have a 2 to the third power. If we had 2 more 2's multiplied by this 2, that would give us a 2 to the fifth. So I'm going to go over here and multiply 2 squared times this denominator. This 2 to the third times the 2 squared would give us a 2 to the fifth. The 5 would match our index. I can do this as long as I go to the numerator and multiply that by 2 squared also. Okay. Now, for the z, it has a 4 as the exponent, and I want it to be a 5. So if I multiply by an additional z on the denominator, I'll now have 4 plus 1, 5. I'll have the exponent match the root number. I can multiply the bottom by z as long as I go to the top and multiply the numerator by z also. If you'll look at this and think clearly, you'll notice that this fraction by itself off to the side is just a 1. Multiplying by 1 doesn't change anything. We still have an equivalent radical expression. It's just going to allow us to get rid of the fraction inside. Alright, so we have the fifth root. On the bottom, we now have 2 to the fifth and z to the fifth. And on the top, we have a 3w and a 2 squared. All this is multiplied and a z. Now, these terms on the bottom in the denominator will cancel out if we apply the fifth root to them. We need 5 to take 1 out. Now, they started on the denominator, and so they are going to end in the denominator. If we take a 2 out from this 2 to the fifth, it's going to be in the denominator of the fraction. Likewise, the z will also be in the denominator. But now, inside the radical, all we have left is 2 squared is 4 times 3. We have a 12, and we have a w, and we have a z. And we consider this as the simplified version. There's no fraction inside the radical, and there's no radical symbol on the bottom of a fraction. Alright, so this one, we write the square root out. 5 and 3 are both prime already, so we don't have to do a factor tree. I think that says z there. I'm just going to go with a z. I'm not really sure. Now, our index is 2. That means we want 2 of everything. That would be the best case scenario. But specifically, we want 2 of everything in the denominator. We do not want this denominator inside the radical because that makes a fraction. We need 2 3's and we only have 1. So we go over here and multiply by 3 on the bottom. We want this exponent to be divisible by 2. So we throw in another y. Y times a y to the 7th is a y to the 8th. We like 8 because it's divisible by 2. Now, the z, we multiply by an extra z. A z and a z makes a z squared, and a 2 is divisible by 2. We only want to add just as much as we need. If we multiply the denominator by 3yz, we also have to multiply the numerator, or else we're changing the original radical expression. As of right now, this radical expression is equivalent to the original one. Now, on the bottom, we can write 3 squared, y to the 8th, and z squared. On the top, we can multiply 3 and 5 together to give us a 15. And then we have an x to the 3rd and a yz. Alright. The purpose of this middle step here was so that we could bring out the 3 from the bottom, a y to the 4th, and the z. All of these exponents on the bottom are divisible by 2. There is no longer a denominator inside the radical. Alright. However, we're not done simplifying because you see, that's not supposed to be a 3 there. I don't know why I wrote the index as a 3. It's a 2. We have enough x's to bring one out on the top. There's 3 inside. We only need 2 according to our index. So we'll bring the x out. And that'll leave inside of our square root of 15 an x, because we only needed 2 of these 3. So 1's left over, a y and a z. And that will complete example 23. Okay, the third way of simplifying is to basically deal with the negative. In the case of example 24, we have an odd index number, so we can just bring the negative out front, and then we're finished with this one. Okay, example 25 is not real. We have a negative inside an even root radical. The next one, we have an odd index number, so we can just bring the negative out and write 5th root of y to the 11th. 5 will go into 11 2 times, so we bring out a y squared, y2. We still have the negative there, and then on the inside we have 1y left over. And finally, example 27, we have an odd index number. We bring the negative out. Inside we have a 16 and x to the 8th. Negative stays outside. We can rewrite 16 as a 2 to the 4th power. And now we can bring out 1, 2, because there's 3 of them. We have 1 left over on the inside. 3 will go into 8 twice, so we bring out an x squared. And so inside the radical we have a 2 left, and then we have an x squared left. Okay. We used up 2 groups of 3 from the x to the 8th. We used up 6 of them to make this x squared on the outside, so there's only 2 left on the inside. And that completes example 27. last way of simplifying radicals is sort of like simplifying fractions. If there is a common divisor between the exponents and the index number, then we can simply divide it out. 8 and 6 are both divisible by 2. So if we divide both by 2, we can reduce this to a fourth root of a to the third power. This next one is sort of subtle. We have a fourth root of 9, but 9 can be written as a 3 squared. Okay, so it's probably a good policy to take your numbers and write them in prime factor form. 4, the index, and the exponent 2 are both divisible by 2. And that's exactly what we do to simplify this expression. Divide the root number and the exponent by 2, and that will reduce this to a square root of 3. Finally, we have a sixth root of 3 cubed and a z to the 9th. 6, 3, and 9 are all divisible by 3, and so we'll do that. And we end up with 6 divided by 2, or 6 divided by 3 is 2, so we have a square root. 3 divided by 3 in the exponent leaves us with a single 3, a 3 to the first power, and 9 divided by 3 for the z in the exponent would be a z to the third power. Now, we're actually not finished simplifying this one because we have a square root. The number here is 2, and so we have plenty of z's to bring 1 out to the front. Z to the front, and 3z left inside. On the next page, what we're doing is adding radical expressions, adding and subtracting them. And the rule is all of the index numbers have to be the same before you can add the radicals. Okay? And by adding the radicals, we're not actually going to add the numbers inside the radicals. We're not going to add the index numbers together. We just sort of consider the radical part to be like a common denominator. Alright, so when you look at example 31, you should see something that is similar to a 2x plus an 11x minus a 7x. If we were given this instead, 2x plus 11x minus 7x, we would just keep the common variable part x and carry out the operations with the numbers. 2 plus 11 is 13, minus 7 would give us a 6. So we'd write down the 6 and just put a single x to the side. That is exactly the same thing that we do with this radical expression, except instead of an x, we have a fifth root of 9. So 2 plus 11 minus 7 is a 6, and so we have 6 fifth root of 9. Alright, but in order to do this, we have to have the root numbers the same, and we also have to have, and I didn't mention this, and I should have, we have to have the radicands the same. Same index and radican. Else you can't add or subtract the two radicals that you're dealing with. Alright, 32. This is a square root. That is a square root. but the numbers inside do not match. Alright, so we don't just throw up our hands here and say we can't add them. It turns out that what we need to do is write out each number in prime factor form and simplify the radicals. If you do a factor tree, 12 is 3 times 2 squared. 27 is a 3 cubed. Alright? Now, with a square root, that means we are looking for two factors, two of the same factors inside, to bring one out. There's two 2's, so we bring out a 2 and multiply it by this 5, and there is a 3 left over inside. For this next radical, we have 3 3's, and we only need 2 to bring one out, so we use up 2 of them, and so there's 1 left over inside the square root. Now our indexes match and our radican match. We have 3's inside the radicals. We have to multiply these numbers 5 and 2 to get 10. 2 times 3 is 6. 10 plus 6 is 16, and so we've combined these two radical terms into a single one. We keep the common radical part, square root of 3. And so this would be our final answer. So if at first the indexes and radicans don't match, then maybe you should simplify the radicals. Alright, the next one, we have a cube root of 81, which 81 is a 3 to the 4th power. We have a cube root of 24, and 24 is a, let's see, a 2 to the 3rd power times a 3. Alright, if this doesn't if this isn't obvious, then what you need to do is a factor tree, and you should know how to do a factor tree at this point. Alright, now we have exponents in each radical that are equal or bigger than the index 3. So we have some simplifying to do. We've got 4 3's, so we can take 1 out. That leaves 1 inside out of the 4. The 3 that we brought out to the front of the radical multiplies the 2 that was there. Now for the second radical part, we have 2 to the 3rd, and we need 3 of something, so we can bring out a single 2 to multiply by this 3 in the front, and the 3 is left inside. So now you see that our radical parts are identical. So we just keep the 1, and then we combine the numbers in front to get 2 times 3 is 6, minus 3 times 2 is also 6, so 6 minus 6 gives us a 0, and then that's multiplied times this radical part, but 0 times anything is just going to be equal to 0, so all of this stuff canceled out. If we look back, these two radical expressions were actually equal, so we get a 0 in the end. The last one on the page, we look at the first radical, and we have a 4 and a 2 for the index and the exponent. Both 4 and 2 are divisible by 2. So we'll divide both of them by 2. And then likewise, the 6 and the 3 of this second radical, they're both divisible by 3. So we'll divide that out. and we end up with a square root of z plus square root of z. Alright, the number in front, just like an x, just like a single variable, the number 1 is understood to sit in front of each of these radicals. So we have 1 plus 1, 2 square root of x. Okay, this next one, we're simply multiplying. On the previous page we talked about adding and subtracting radical expressions. Now we're talking about multiplying and dividing. Only thing that needs to be true in order to multiply two radicals is that they have the same index. Alright, so we have a square root, and we just write 8. We multiply the radicals and put that inside of a single square root. And so what we have here is a square root of 48. Now we're told to simplify our answers also. So we need to prime factor 48. Alright, and what we end up with in the end is 2, 1, 2, 3, 4, 2 to the 4th power, and then a 3. Okay, so we replace the 48 with this prime factor form that we found. With this being a square root, this number is 2, and 4 divided by 2 gives us 2 2's on the outside, and the 3 is left over on the inside. So in the end, this becomes a 4 times the square root of 3. Okay, 36, we have a 5 and a 5. We can combine these under one single 5th root radical. 2 times 3 is 6. X to the 3rd times x squared is x to the 5th. Y squared times y squared is y to the 4th. Now, there are 5 x's. That exponent 5 matches our index. That means that we can bring out 1x to the front. All of the other exponents are less than the 5, so we're left with a 6y4 inside the radical. And that completes example 36. On the next page we have division. We can write this in a single cube root radical and simply combine the 72 and 9 into a fraction. 72 divided by 9 inside is an 8, and the cube root of 8 is a 2. We have the 4th root and the 4th root, so the indexes match. We can write this in a single radical with x to the 5th y on the top and xy on the bottom. Working from inside the radical, this x cancels out one of these on the top to leave us with the x4. Okay, 5 minus the one on the bottom is a 4, and then these y's just cancel each other out, and so there's no y's left inside the radical. Now our index matches the exponent, and so this reduces to a single x. last page of the chapter, we have a 3 square root of 2 and a 4 square root of 6. We want to combine these as a single radical. Now, we can't just multiply the 2 times the 6 because these indexes are different. Okay? So we can't multiply 2 times 6 and put it under a single radical. There is more work to do before we get to that point. What we're going to do is rewrite these radical expressions as exponential ones. Okay. And now that we see that the indexes are just simply the denominators of the exponents, we still won't be able to combine the 2 and the 6 because they're different bases, but it's easier to see now that these are written as fractions that we can change the denominators. Okay, we will write find a common denominator of 3 and 4, and that would be 12. And so here, when we have the same denominators, that simply means that when we convert it back to radical form, we'll have the same index numbers. So if we fix these fractions, we fix our problem. 3 goes into 12 4 times, so this is a 4/12 for the 2. And 4 goes into 12 3 times, so a 3/12 for the 6. Now, like I said, we can't multiply, we can't just add these exponents together because the 2 and the 6 aren't the same base. But we can convert this back to a radical. And when you do that, you see that now the root numbers are the same, but our 2 and 6 now have exponents 4 and 3. So with the indexes the same, we combine them under a single radical with the index of 12, and we write 2 to the 4th times 6 to the 3rd power. We can pull up our calculator to see exactly what that number works out to be. 2 to the 4th times 6 to the 3rd. Enter. 3,456. So this is the 12th root of 3,456. Alright, moving down the page to our last example. We have 3 to the 2/3 and 2 to the 1/5. We can't combine these two expressions into a single exponential expression, but we can see that the indexes are just denominators that can be adjusted. So common denominator of 3 and 5 is 15. 3 goes into 15 5 times. 5 times the 2 would give us a 10. And 5 goes into 15 3 times. 3 times 1 is a 3. Now, these translate back into 15th root radicals, with the 3 having an exponent of 10 and the 2 having an exponent of 3. Now we combine them under a single radical, and we have 3 to the 10th times 2 to the 3rd. And if we want to write that as a single number, we'll pull out our calculator again, calculate 3 to the 10th and multiply that by 2 to the third, which is an 8, we get a big number. Let's see, 15,116,554. Alright, so if you want to write this in your workbook, here we have it. 15th root of 15116,544. Alright, so there it is. That's our last example. What you can do is just go back, maybe try to rework these without looking at the workbook. Definitely go back and study the examples that were just given to you, already worked out in the workbook. Of course, if you have any questions, you can come by my office. Thanks for watching.